This is part 2 of the video lecture for Math 181 for Tuesday, April 28th. And the topic for today is calculating the volume of a solid object using the method of cylindrical shells. And in part 1 of this video lecture, we derived this formula for the volume of a solid object of rotation using cylindrical shells. And now we're going to apply this formula to solve two specific examples. The first example is the example I gave you guys at the beginning of part 1 of this video lecture, which was the justification for using the method of cylindrical shells. It was a cubic function y equals x minus x cubed. And we talked about this function. We tried using the standard way of calculating the volume by disks, by horizontal slabs, and disks created by rotating that around the y-axis. So we're going to take this curve, rotate it around the y-axis, create a three-dimensional solid object that'll look kind of like a donut, and we want to calculate the volume of that object. But we argued that this was very difficult to do using the traditional method of horizontal slabs rotated around the y-axis, creating washers, okay? Because it's hard to solve this equation for x. But now we're going to use the method of cylindrical shells. It sounds sort of like an infomercial. Just for $19.99, you can use the method of cylindrical shells and your life will be wonderful. But it will be wonderful. So what we're going to do again is divide up this curve into a series of rectangles. Imagine rotating each rectangle around the y-axis. That'll create a series of nested cylindrical shells. And we're going to calculate the volume of this solid object by summing up the volume of all the cylindrical shells. We can use this integral to do that. And let's go ahead and do it. So all we need to do is just do this integral, the integral from 0 to 1, because we're interested in this curve from x equals 0 to x equals 1, where it hits the x-axis. Okay. So we integrate from 0 to 1 of 2 pi times x times f of x. In this case, f of x is x minus x cubed, okay, times dx. All right, so we need to integrate this function. Unfortunately, this is quite easy to integrate. We pull out the 2 pi, okay. We distribute the x onto what's in parentheses, and we get x squared minus x to the 4th dx. Okay, and now we integrate this. This comes out to 2 pi times the integral of x squared is x cubed over 3. The integral of x to the 4th is x to the 5th over 5. And then we evaluate this from 0 to 1. And we're trying to find our volume here, so our volume will equal 2 pi. Now if we plug in 1, our upper limit, 1 cubed is 1, so we get 1/3. 1 to the 5th is 1, we get minus 1/5. Okay. And then if we plug in the lower limit, that's just 0 because we have powers of x here. So the lower limit is just 0. So this is our volume, and what we can do is find a common denominator, which is 15. So we can rewrite this as 5 over 15 minus 3 over 15, which equals 2 pi times 2 over 15. And this equals 4 pi over 15. So this is the volume of when we take this curve and we rotate it around the y-axis. But we calculate that volume using the method of cylindrical shells. So sometimes the method of cylindrical shells is a better, easier method to calculate the volumes of objects. Let's do another example. Erase this. Okay, in our second example, we're going to calculate the volume enclosed by two curves when an area enclosed by two curves is rotated around the y-axis. So in this case, we're going to calculate the volume of the two curves y equals x squared and y equals square root of x and y equals x squared. If we rotate the region enclosed by these curves about the y-axis, we're going to calculate the volume So we have these two curves, and these two curves enclose a certain area, okay, or close a certain region. And if we rotate that region about the y-axis, that will create a solid object. We're going to calculate the volume of that solid object. A first good step here is to create a graph of these two curves. So let's do that. Okay, y equals square root of x. We know what that looks like. It looks like this. And y equals x squared is a parabola. We know this looks like this. And this encloses a certain area here. And we've done this problem a whole bunch of times before. You know how to find the area of the enclosed region. So this encloses a certain region. What if we now were to rotate this enclosed region about the y-axis, right? This would create some kind of solid object. It would have kind of a funny shape. It'd sort of be like a bowl shape, but it'd be like a weirdly shaped bowl that has it's thicker in the middle here, and it has a thinner walls, be hollow on the inside, but thinner walls as you go up to smaller or larger values of y. So I'm not going to attempt to draw what that object looks like, but just imagine rotating this enclosed region about the y-axis. It will create some solid object. We're going to calculate the volume of this solid object. Okay. So first thing to do here is we need to find this point of intersection. What is this point of intersection? And we've done this before, but let me show you guys again how to do this. The way we do that, point of intersection, the way we do that is we set these two curves equal to each other. So we get square root of x equals x squared. We square both sides, which leads us to x equals x to the fourth. Okay, then I'm going to move the x over to the other side, so I get x to the fourth minus x equals 0. And then I can pull out an x here. And so I pull out an x, I get x cubed minus 1 equals 0. And this means x equals either 0 or 1. These are our 2 points of intersection. So one point of intersection is 0, 0. The other point of intersection is 1, 1. So now we have our limits of integration. And we can simply do this integral. The volume of the region enclosed, the volume of the solid object created by rotating this enclosed region about the y-axis is equal to the integral from 0 to 1 of 2 pi x. Now here's a question. What should we put in for f of x here? Okay. Well, let's look at this. We're going to divide this region into, let me draw this in red. We're going to divide this region into rectangles. So here's a typical rectangle here. And we're going to rotate this rectangle around about the y-axis, creating a cylindrical shell. Now, what is the height? What is the height of this rectangle? Well, the height, if you guys think about it, the height here is, this height is square root of x. Okay, and this height right here is x squared. So f of x is simply square root of x minus x squared. The height of this rectangle is the height of this top curve minus the height of the lower curve. And so I know that f of x equals square root of x minus x squared. Okay, so I can plug that in for f of x here. And so I get square root of x minus x squared is the height of my cylindrical shell, okay, times dx. And now I can evaluate this integral. I can pull out the 2 pi. I'm integrating from 0 to 1. I can distribute the x onto what's inside the parentheses. And if we do that, this is like an x to the 1/2. So I'm going to get x to the 3/2, right? X times x to the 1/2 is x to the 3/2. X times x squared is x cubed dx. This is what I get. And now this is a straightforward integral. I'm going to perform it. So the volume equals 2 pi. And now I get x to the 5/2 over 5/2 minus x to the 4th over 4, evaluated from 0 to 1. I'm just going to clean this up a bit. This is going to be 2 pi times 2/5 x to the 5/2 minus x to the fourth over 4. Let's distribute that 2 pi. So this comes out to pi times 4/5, right, x to the 5 halves, minus, one of these 2's cancels, minus 1/2 x to the 4th. Let's make sure I'm on the right track here. And if we do this, we plug in the limits now, evaluated from 0 to 1. If we plug in our limits, we get pi times 4/5, and then x, 1 to the 5 halves power is 1, minus x 1 to the 4th power is 1, minus 1/2. Okay, if we plug in 0, we get 0. And so I can try to find a common denominator, and it looks like I'm going to get 10 here, right? So this would be 8/10 minus 5/10, and this comes out to 3 pi over 10. 3 pi over 10, and that is that's the volume obtained by rotating this enclosed region about the y-axis. So this is a really cool application of cylindrical shells, and that concludes part 2 of our video lecture. I'll see you guys on Tuesday.